Okay, we're ready to start talking about atomic structure. And we're first going to talk about the Bohr model of the atom. You're probably familiar with this model of the atom if you've seen pictures of the atom that have sort of a dense positive nucleus with electrons orbiting around the nucleus. This is essentially the Bohr model of the atom. And I don't want you to get too used to thinking about the atom in this way. I mean, sometimes we'll think about the atom like this, but don't get too used to it because, well, there's a better way to think about it, even though this is often useful. The Bohr model was particularly successful in describing how the hydrogen atom behaves. You see, when hydrogen atoms get excited, they give off light at 656 nanometers, at 486 nanometers, at 434 nanometers, at 410 nanometers, among other wavelengths of light. And Bohr, in his model, was able to perfectly describe why hydrogen gives off light at these particular wavelengths or these particular colors of light. He did so by assuming that the electrons in a hydrogen atom were quantized. That is to say that the electrons could have certain energies, and those energies were described by this equation. The energy of an electron in the nth shell, we'll call it, the nth shell, where n can be equal to 1, 2, 3, 4, any integer. We'll say like an electron in the first shell, stick the electron in there. The energy of that particular electron is going to be negative 2.18 times 10 to the negative 18 joules divided by the shell number squared. So that would mean that this electron here in the first shell would have an energy of negative 2.18 times 10 to the negative 18 joules divided by 1 squared, which is just 1. So that's the energy of an electron in the first shell. And you might ask, well, why is this negative sign here? Well, the way it was envisioned is if you take the nucleus and you imagine pulling an electron an infinite distance away from the nucleus, we'll call it n equals infinity, that's given an energy equal to 0. And then as that electron gets closer and closer and closer to the nucleus, then its energy is going to drop, of course, because the electron wants to be on top of the nucleus because of Coulomb charge, right? A negative charge and a positive charge, those want to attract one another. So, of course, it takes energy to pull an electron away from the nucleus. And so if that electron moves towards the nucleus, energy is going to be released. And therefore, if we take that electron and we drop it all the way into the n equals 1 level, then its energy is going to be negative. And of course, we just showed that that's going to be negative 2.18 times 10 to the negative 18 joules. Now we can use this model in the following way. Let's go ahead and draw our n equals infinite level here. And we'll draw the n equals 1 shell here. We sometimes call shells energy levels as well, so I'll use those two terms synonymously here. Then a little higher up, we're going to have the n equals 2 shell. Higher up is the n equals 3 shell. Higher up, the n equals 4 shell. A little higher up, the n equals 5 shell, and so forth. The shells continue to bunch up as you approach the complete separation of the electron from the nucleus. And we could calculate the energies of all these levels. Of course, we just showed that the first shell is going to be negative 2.18 times 10 to the negative 18 joules divided by 1 squared. Because we have this equation, the energy of the nth level is going to be minus 2.18 times 10 to the negative 18 joule divided by n squared. So the energy of our second shell, an electron in the second shell, that's going to be negative 2.18 times 10 to the negative 18 joules divided by 2 squared, which is 4. The energy of an electron in the third shell, what should that be? Well, that's going to be negative 2.18 times 10 to the negative 18 joules divided by 3 squared, which in that case we'll divide by 9 for the n equal 4 shell. Let's just call this E. We'll call it EH for E hydrogen. We're going to call that negative 2.18 times 10 to the negative 18 joule. And if I do that, I can make these energies that I'm calculating here, the symbolism of it, a little more compact. So E4 would simply be EH divided by 4 squared, which is divided by 16, and so forth. And what this allows us to do is it allows us to calculate how much energy it's going to require for an electron, let's say, in the hydrogen atom to, let's say, get promoted from the n equals 1 to the n equal 2 shell. How much energy would it require to take an electron and do that? We can calculate that. We know that E2 is EH over 4, and we know that E1 is EH over 4, where we're going to remind ourselves that EH is negative 2.18 times 10 to the negative 18 joules. And so if I want to find this change in energy, if an electron is going to move from the n equal 1 level to the n equal 2 level in hydrogen, let's see, we want to calculate the change in energy. That's going to be equal to the final energy minus the initial energy. And if we're moving from the n equal 1 to the n equal 2 level, our final energy would be E2, and our initial energy in this transition would be E1. So that means we can calculate delta E. That's going to be E2, EH over 4, minus E1. Oh, I put EH over 4 here. That should be EH over 1, shouldn't it? So let's see, that'll be minus EH over 1. That'll be my change in energy. We can factor out the EH, but that'll be a quarter minus 1. Well, that's pretty easy. A quarter minus 1, that's a negative 3/4, isn't it? So my change in energy should be whatever this EH is times negative 0.75, which we can easily calculate because we know what EH is. Negative 2.18 times 10 to the negative 18 joules times a negative 0.75. We're multiplying two negatives together, so the change in energy is going to be positive. And that makes sense because it's going to require energy to move the electron further away from the nucleus, to move up an energy shell. And now we just calculate this particular energy change here. 2.18 times 10 to the negative 18 times 0.75. That's going to be a positive 1.635 times 10 to the negative 18 joules. Now, in order for an electron to make this transition, it's going to need to gain energy from somewhere. And usually what happens in atoms is they gain this energy from, or I should say often, they gain this energy from a photon. So we can have a photon of light come in here. I should have it come this way. The electron absorbs that photon and gets promoted. So we can actually calculate what is the energy of this photon that's going to be required to cause this transition. Because remember that E is h nu for a photon. So we can calculate the frequency of that photon, or if we remember that nu is c over lambda, and plug that in, E equals hc over lambda. If we know the energy required for the transition, which we do, of course we know Planck's constant and the speed of light, we can find the wavelength of the photon that's going to need to be absorbed to cause this particular transition.